Hi, my name is Nguyen and I am a research assistant from Dr. Marizi Rigolab. And today I'm in charge of presenting our project published at the ISAP conference on September last year. The main objective of this project is to analyze and validate a cyber resilient control for a 100% inverter-based microgrid using real-time simulation. The US has an ambitious plan of reaching 100% clean generation by 2035. The growing number of inverter-based resources or IBRs such as wind or photovoltaic is very essential to achieve a complete renewable integration. And for that, improving the resiliency of a 100% inverter-based microgrid is a critical step in achieving such a goal. IBR can be controlled in grid forming or grid following mode. In the context of this project, the main focus is on the grid following IBR. GFL IBR rely on communication devices such as remote terminal unit to receive real and reactive power setpoint from a SCADA system. Because of that, GFL IBRs are vulnerable to cyber attacks. A prime example of cyber attacks on the grid is the 2014 cyber attacks on the Ukrainian power system, leading to a massive blackout of 225,000 people. Currently, there are studies that propose methods for detection and mitigation of cyber attacks on the grid, but most fail to validate the method for feasibility in real-life applications. The control scheme used in this project is a long short-term memory or LSTM base used for detection and mitigation of false data injection attacks such as RAM or bias attack on the set point of GFL IPRs. LSTM is a machine learning model that is used to predict time series data, which is very suitable for our purposes. The figure to the left here shows an LSTM layer with forget input as well as the output gate. To the right shows the detection method we use. With HPNQ setpoint would have an LSTM layer that would take in the grid measurement data, as well as a receive setpoint that is sent to the IPR to output an estimated setpoint, and the differences between the estimated setpoint and the received setpoint would then be used to detect whether or not an attack has occurred. We also created a control hardware in the loop consists of a PC as the SCADA system, a Raspberry Pi 4B as the controller, the Typhoon Neo 402 real-time simulation hardware, and software to simulate the power system layer, and to conduct the FDI attacks as well as using a network switch and the user datagram communication protocol to create a communication channel. The control scheme was tested on a 100% inverter-based 4-bus microgrid with the configuration shown on the left and the grid parameters shown on the right. The detection and mitigation scheme is ran every 6 milliseconds to provide a fast and reliable response. The attackers can cause over or under voltage by using attacks such as positive or negative bias or RAM attack on the reactive power set point, with the RAM attack being more difficult to detect due to its incremental nature. The figure to the left here is the simulation result for the positive RAM attack case, where the reactive power set point of the number 3 GFL IBR is increased from 60 kV to 1 MV by 9.4 kV every 10 milliseconds. As you can see, without any detection and mitigation scheme, the voltage at the terminal of the IBR increased from 1 to 1.07 per unit, with the 7% overvoltage. However, without a control scheme, the voltage was not allowed to exceed 1.01 per unit, and the IBR recovered its nominal operating condition after 0.75 seconds. For the case of the positive bias attack, the Q set point would change from 60 kV to 1 MV. Without any mitigation, the attacker can cause a 7% overvoltage. But with the proposed method, the inverter can recover within 42 milliseconds after the attack with a maximum overvoltage of 2%. As for the negative bias attack case, with the Q set point change from 60 kV to negative 1 MV, without any mitigation, the voltage is dropped to 0.9 per unit, but with the proposed method is applied, the controller is able to restore its function within 50 milliseconds after the attack, and the voltage not dropping below 0.96 per unit. And that's it. Thank you very much for listening, and feel free to leave any question, comments, or feedback.